So welcome again, everyone, to this UK CMIP6 workshop. So hopefully many of you were with us yesterday, but we are holding these online poster sessions as a sort of forum for discussion. And we've had, yesterday we had a lot of excellent posters, so thank you very much to those presenters. We've got a really good lineup again today for the two sessions. So this one for an hour now, and then another hour at 1 o'clock. And our plan is to hold some further ones of these in May, and we're deciding on those dates at the moment, so we'll let you know. So in this session, there'll be 5 short presentations, followed by a few minutes of Q&A at the end of each of the presentations, and I will moderate the questions. So if you'd like to raise a question or make a comment during the presentation, please use the chat facility in Zoom. If we don't have time to answer all the questions, then we will capture them in the Google Docs document, the link of which was sent out to everybody, and you're welcome to add a bit more information to these documents to aid the further discussion. We're recording these poster sessions, and the plan is to put them on the UKSM website. Details of that will be sent out when it happens. Please keep your microphones muted throughout as we try to reduce the sort of bandwidth, and so we will be sharing our screens, but please turn your videos off. Okay, and so today's session starts with the first talk that is by Lee Demora, and his talk is titled Earth System Music, the Generation and Reach of Music Generated from the UK Earth System Model, UKESM1. Over to you, Lee.
Yes, hello everybody, good morning. So just to get us started, see if I can get to my first slide. Did that work? It didn't work, okay. Okay, here we go, yeah. So yeah, as already mentioned, I'm going to be talking about Earth System Music. It's a little project we did about using UKSM data to create music. So the key thing about this is that it's becoming increasingly important that we try to engage and interact with the general public, especially in ways that we can help them understand how our models are put together, and not just the results, but also the methodology. But it's also simultaneously becoming a lot easier for scientists to use social media to interact with non-expert audiences. So the idea for this project was generated last summer at the Blue Dot Music Festival with a UKESM. We had a stall there. It's a science and music festival. So we had very good interaction with people about the science, but we thought it'd be quite interesting to see if we can also create some music. So what we did was we built this pilot study called Earth System Music, where we tried to use the sonification to interact with people. So sonification is just the use of non-speech audio to convey information. In science, this is long-standing practice, with the most famous example being the Geiger counter, which clicks in the presence of ionized radiation. But sonification is also very common in monitoring in medicine. So what we did is we generated 7 musical pieces with data from the UKSM's ocean component model. And we tried to cover a really diverse range of scientific and musical contexts. So we cover the spin-up, the pre-industrial control run, historical and future scenarios. Continuing, so we try to cover the ocean, like different aspects of the ocean model. So the circulation, the carbon cycle, the sea ice, the temperature, and some aspects of ocean acidification. And musically, we also cover quite a wide range with an allegro, a vivace, 4-chord song, a 12-bar blues, a minor harmonic aria, a version of Lizzo's song Juice, and a version of Pachelbel's Canon. So before we start to play this track, you may need to adjust the volume on your headset. Hazel, could you please start the video? Right. Yep. Thanks a lot for that, Hazel.
Thank
I
you.
believe there's a clap button in the chat if you want to use that. So yeah, so you probably recognize the sort of happiness of the CGA minor F progression. And we chose this chord because it should feel very familiar to people. And we're trying to, I mean, this was the first piece that we produced in the project. So we really want to try to avoid alienating the audience. We're using happy chords, and hopefully that should be also reflected as the, we use the SSP 1.9 scenario, which is the gentlest possible climate change, 1.5 degrees warming by the end of the century. Could we go to the next slide now, please? The method is fairly straightforward. We take the, there we go, there it is, okay. So we take the model data from UKESM in its CDF format and pass it through the BGC eval, which is a model evaluation toolkit. We then have these time series data that is effectively just, well, it's in shelf format, but it doesn't really matter what format it is. It could be an ESMval tool or anything. Or we also have this Python dictionary of processor settings for the music part, and that will contain all the artistic choices and the paths and the required data sets and things. So we load that and the data. We apply a smoothing to, well, optionally apply a smoothing to remove some of the variability. We convert the model data into pitches. Then we enforce a choice of scale or chord progression. We set the MIDI velocities. Now, velocities basically just means loudness, so how loud it is. And that's also set with a data from UKESM. We remove the duplicate notes. So what that does is if the same note occurs twice in a row, we remove the second one and extend the first one. And then at the end of the piece, we just hold the final note of the chord so it doesn't end abruptly. And using the data, we've also produced one frame for each time step in this piece. And we also saved the final notes as a musical instrument device interface MIDI file. So from there, we convert the MIDI and the images into a video and put that straight up on YouTube. We can also save the MIDI files as a piece of sheet music if necessary. So going to the next slide. Did that work? Let's try. Okay, yeah. So this image just kind of describes how the ranges of the different data sets appear in the piece, with the Drake passage current having the highest range because it's always easier to hear the highest notes in a piece of music. And the other three data sets just show the ranges of those data sets, how they vary within that range. But what's interesting here is you may notice that the Drake passage current can play any of the notes in the C major scale, whereas the other three data sets are only playing the chords. So it shows here C major, and those are the notes that are available for those data sets. So we have an interesting way to separate the melody from the backing track, effectively. And of course, the choice of notes for the three backing sets depends on the modulation of the chord. So as it goes to G, the notes will change, for instance. So these are the artistic decisions we need to make in order to produce a piece. The choice of the data set, the velocity and the pitch, the width of the smoothing window, the tempo, the key, the chord progressions, the choice of instrument. I mean, so far we've only used piano, but other synthesized instruments are available, and the title and the style and the final mastering. But the idea behind these this artistic decisions is that it should allow the composer to attempt to define the emotional context of the piece. For instance, we already saw the SSP 1.9 should be fairly optimistic and free-flowing, but some of the other pieces we looked at, the SSP, well, we've created, like for instance, looking at SSP 8.5, that could be uneasy and foreboding, for instance. So we kind of hope to define the context in that way. We also looked at the reach of this work. So once we produced the videos, we posted them on YouTube, and I simply shared them via my personal and professional social media. And from there, we track the view count and the demographics using YouTube's own toolkit called YouTube Studio. And we also keep track of the comments from audience. So I've got three figures here. The first one shows the number of views since since the start of the project for each video. And it's quite clear the piece that we show in the first one is the one that had the most views overall and when it opened. And we got increasingly fewer views per video as they were released. the total views per country, unsurprisingly, the bulk of them are from the UK. And then similarly, the third plot is the traffic, where we see that most of the views come from externally. So people finding something on Twitter or Facebook or Reddit and then going to see it. And so, I mean, in total, we got 525 views in the first 90 days and about 250 unique viewers and just under 8 hours of watch time. So while we didn't get the millions of subscribers of some of the bigger YouTube channels, we also, the only other YouTube video on YouTube, UKESM video, sorry, on YouTube, only has 220 views and was published in 2017. So in contrast, compared to other YouTube channels that are about climate science, we're doing all right. I mean, the most popular video with Earth System Model in the title only has 5,000 views. So at the moment, with our 1,400 in 6 months approximately, we're doing all right. And there's also been lots of discussions about possible ways to extend this work, including live performances, adding different instruments, new styles, extending the data available, so different models, domains. It'd be nice to look at the atmosphere, for instance. We could do that if we used ESM Val tool instead of BGC Val. We could include observations. One of the really useful things to extend the analysis of the reach would be to create a viewer survey, because at the moment we don't know if our viewers are experts or laymen. And we could also, so hopefully we could engage with people more in that way. But there's a paper upcoming and there's several more videos to look on the YouTube channel, and I invite you to go have a look there, like and subscribe and share. And finally, I'd just like to encourage everybody to think about sonifying their data. There might be some really unique and beautiful music hidden within your data sets. Thanks.
Thanks very much, Lee. That's great. Sorry about the technical issues there, but really nice to hear that. There's a lot of questions on the chat, but I'll just sort of very quickly paraphrase them. Please do look at them in the Google Docs document. So there was quite a few people asking whether you've had any feedback. I think you commented that you've had a lot of people looking at it. Has anybody actually responded?
Yes, we've had, in general, there's a discussion around this topic whenever it's shared. And we received several comments. Some of the more interesting ones were actually on a piano Reddit page where they discussed the, how a human performance might be impossible, but might also add quite a lot to the sort of the subtleties of a human performance, in terms of changing the timing slightly and adding a bit more depth and feeling to it. So yeah, there's been quite a lot of interesting comments coming out of this.
And
a couple really negative ones.
Have we learned anything scientifically? That's another question that people, or will we?
Scientifically, I wouldn't say that there's any new resources. I mean, any new insight into the model this way.
Okay.
Unless you just count spending more time looking at the data.
I guess that has some value. People were suggesting using, doing the same thing with the obs and then comparing them, whether one sounded like the other, that sort of thing. But anyway, I think we have to move on. So thanks very much, Lee.
Yep, thanks, everybody.
Thank you. So our next speaker is Pat Hyder, and he's going to talk to us about CMIP Southern Ocean SST biases, tracing them to cloud errors. Over to you, Pat.
I can't see the bar. I don't think I've been given control yet. That's it. I've got it now. So great. So my talk's going to be rather dull by comparison, I think. Let me see. Yeah, it's moving. So I'm just really presenting a few slides from some work that was published about a year ago, and then to try and just inform people what we've been working on more recently. I've got a summary slide at the end with ongoing work. So it's mainly focused on Southern Ocean warm biases, and most CMIP 3 and 5 coupled models have Southern Ocean warm biases, and some new theory given assumptions that the atmospheric fluxes dominate over the ocean ones suggests that atmospheric only net flux biases should be a key driver of equilibrated coupled SST biases. And that's indeed what we find. The figure on the top left shows that the correlation between AMIP net flux biases, which know nothing whatsoever about the ocean, and the fully spun up coupled SST biases is 0.84. By contrast, the correlation for the coupled net flux bias with the SST is actually very weak. And for shortwave alone, the correlation is about 0.73, suggesting that these AMIP errors are cloud related. And importantly, though I haven't got a lot of time to talk about it today, the equilibration involves a dominant negative SST dependent coupled surface flux feedback. This is the plot on the bottom right, which shows the amount the flux adjusts when you couple a model against the SST. And this is weakened considerably by the overlying atmospheric adjustment to this flux response. So it's very wrong in ocean only runs. It's far too strong. So the other thing that we worked on is we looked at the AMIP net flux and broke it down into the components and found a lot of error cancellation between the different heat flux components within the different AMIP5 models. So the conclusion from this is that most good net flux and SST models achieve it through error cancellation between the components. And to show this, we define this parameter called TAFB, or total absolute flux bias, which simply adds up the absolute short wave, long wave, and turbulent flux biases. So if you like, it's a measure of error cancellation, first order. And to be confident in a model's future response, you obviously need a good TFB and net flux. And what we find is that most models with a good net flux, which is on the y-axis, do not have a good TAFB, which is on the x-axis. And few models are good for both TFB and net flux. So obviously, this has some implications for how much we can trust the models in the Southern Ocean. And another plot, which is I quite like, is that over 20 years, so this plot, the blue line is the Hadley Center model. This plot, that the first point towards the center of the plot is HADCM3, then you've got HADGEM1, HADGEM2, the first HADGEM3 model, and then the CMIP model finally. And what you can see is that we initially made the model net flux biases a lot worse by removing cancelling component errors. And then in the last few years, we've managed to reduce net flux errors for the right reason, without also reducing the TAFB. So on to a bit more on how we did this. I should have said that last plot showed the quarter degree N216 Orca HADGEM3 GC 3.1, and the two panels in red, the top one's SST bias for the coupled model, and the bottom one is the AMIP net flux bias. And what you can see is we reduced the net flux bias by about 65% and the coupled SST bias by about 75%. And we did this through targeted developments, including a new mixed phase cloud scheme, GLOMAP mode aerosol scheme, and tuning to see in late 2018. Having said this, the Southern Ocean issues are by no means fixed in the CMIP6 model. We have remaining cloud and ocean related SST and sea ice models, which cause very large ACC and Antarctic shelf problems. The latter mean that we can't currently run the active ice shelf model. Ice drying and dust dependent ice nucleation, as well as ocean model some dynamic sensitivity work, so subgrid scale closures to try and reduce both the error and what we see is a considerable ocean model resolution dependence in our resolution hierarchy of models. So as to in progress CMIP6 related analyses, one thing that I've been working on that there wasn't time to show today is some global extensions to the regression AMIP CMIP5 analyses to understand drivers of SST and SSS biases globally, and these have very promising results. For SST, we can explain quite a large fraction of the world's SST bias if we consider both local and remote AMIP net flux biases.
2 minutes, Pat.
There's also a lot of work to understand these remaining, yeah, it should be fine. There's also a lot of work to understand these remaining Southern Ocean biases and to reduce them for the CMIP7 model in UKESM2. In particular, we're doing targeted ocean and cloud-related developments which aim to address several linked remaining Southern Ocean problems, all of which vary quite a lot across the ocean resolution ensemble. So these include the remaining SST bias, particularly south of 50, which we think is in part linked to supercooled liquid water, but also is very resolution dependent. It's very much smaller in the 1 degree than the 1/4 degree model that I've shown today. Linked to this is low sea ice and low freshwater transport away from the continent, Antarctic shelf and Weddell Sea salinity bias. Says these cause spurious deep convection in the Weddell Sea polynya, and we have a very weak ACC result, which is linked to a spurious counterflow around Antarctica caused by very fresh coastal biases. And the counterflow causes cold water to move around the Antarctic Peninsula through Drake's Passage to the West Antarctic ice shelf, which mean that the biases prohibit the use of the active ice shelf model. So I guess the key lesson for this is that Southern Ocean is a key region for climate, large fraction of the heat and carbon uptake, but it's extremely coupled both across the ocean and atmosphere and within the different components of the ocean ice system. So any biases spread. So thanks.
Thanks very much, Pat. A couple of questions on the chat. So Matt Collins is asking, are the ice phase clouds related to the increase in climate sensitivity?
No, I should have said, I don't, well, I think they might be, but they're not, I think they are both, the representation of clouds in the Southern Ocean and the stratosphere regions does contribute to the climate sensitivity, but it's not directly related. I should have said these are all just control run biases I'm showing. But I think sort of cloud issues probably cause both, but they're not directly related.
Okay, thanks. From Yevgeny Askanov at NOC. Hi Pat, I think there might be different causes for the sea ice biases in the different Southern Ocean sectors. Have you looked at that?
Well, what we find is that the errors are particularly pronounced in the Weddell Sea sector. And you see this both in the AMIP net flux errors. And I think this is just to do with the environmental conditions there. In the Weddell Sea, the ACC moves north and there's much more sea ice extending northwards, and that means it's much colder. So there's much more potential for supercooled liquid to form in reality, which is not well represented in the models. But also there also seems to be a key sensitivity of the Weddell gyre to the ocean dynamics, and we find scarily large sensitivities in the 1/4 degree model to very subtle changes to grid scale closure in the Weddell Sea. So thanks.
Okay, and just a final one from Siobhan O'Farrell at Access. Are you going to include the Access Southern Ocean bias in the new PEG with the same atmosphere model?
Well, hopefully any cloud-related developments can feed through to the access model. We're very interested in making comparisons with access, and we've been talking with Andy Hogg and people like that about comparing the models. The problems we have is that your latest access version, you haven't run at a quarter degree model, and this is when the problems really seem to be exacerbated. But I have been talking quite a lot with Andy Hogg about this.
Great.
So we find it's actually easier to talk separately rather than within the PEG to Australian collaborators, just for logistic reasons, because of the timing that we need to speak to Australia.
Sure, maybe you can follow that up. And there are a couple of other questions and comments online, so please have a look at those, but we must move on. So thanks very much, Pat. And our next speaker is Matthew Priestley from the University of Exeter. He's going to talk about drivers of biases in the extratropical storm tracks in CMIP6. Over to you, Matthew.
Thank you, everyone. I'm going to talk to you about the extratropical storm tracks in CMIP6. I'm going to give a brief overview as to kind of some evaluation work we've done for both the northern and southern hemispheres, and also a bit of a reasons behind these biases as well. So what we've done is we've evaluated 20 CMIP6 models and identified the storm tracks using 850 hectopascal relative vorticity. And on these figures here on the left, what you can see is the mean state of the storm track from 1979 to 2014 in the models here in the top left. The biases to era 5 here in the middle on the top row, and the CMIP5 biases are shown here in the middle on the bottom row as well. So on first inspection, the biases appear very similar between CMIP6 and CMIP5. Both of them show a equatorward shift in the North Pacific storm track, and also a zonal bias in the North Atlantic storm track here, which extends too far into Europe. Looking at the difference between CMIP6 and CMIP5 here in the bottom right-hand panel just here, what we can see is that the equatorward bias in the North Pacific is slightly reduced, especially in the Western North Pacific, and the zonal bias is slightly reduced in CMIP6 as well across the North Atlantic, with slightly fewer cyclones propagating too far into Europe. However, the main biases do remain. We've also split the CMIP6 models up into a high and low resolution categories. So in this case, high resolution is those with an atmospheric resolution in the order of 100 kilometers, and low resolution in the bottom left here is those with an atmospheric resolution in the order of 250 kilometers. Again, the main structure of the storm tracks is very similar between the two, both showing the equatorward bias and the zonal shift in the North Atlantic. However, we have seen that the magnitude of the biases are slightly reduced with the high resolution models, and the high resolution models also simulate a number of cyclones that's more closely aligned with the reanalyses. So we are seeing improvements with horizontal atmospheric resolution. Another area we're seeing improvement with high resolution is in cyclone peak intensity. So these two figures up here in the top right for the winter season on the left and the summer season on the right. The different lines are different model groups, but what's really of interest is this inset region here on both of them. So the dark blue lines are all the high resolution models, and the light blue lines are all the low resolution models. And the red line is era 5. And what's showing that for high peak cyclone vorticities, so above 10 times 10 to the minus 5, the high resolution models are doing much better at capturing the intensity of cyclones than the low resolution models, and low resolution models are performing similarly to the CMIP5 ensemble. We've also performed some analysis on explosive cyclones in the Northern Hemisphere. These are significantly underestimated in the CMIP6 and CMIP5 models, but we see very big improvements with high resolution in CMIP6 compared to the low resolution models. So a bit behind what's kind of controlling these biases. So the first thing we did was compare the coupled models with the corresponding AerMIP runs. So we've got 16 AerMIP runs, that AerMIP models out of the 20 coupled ones. So this left panel here is the AerMIP biases to era 5. And these are showing a reduced equatorward bias for both the North Atlantic and the North Pacific compared to the coupled models, which you can see especially in this right hand panel here. So this is the 16 AerMIP models compared to their coupled counterparts. seeing a poleward shift of the storm tracks, especially in the western North Pacific and across the North Atlantic. So the zonal bias of the North Atlantic is almost entirely removed, but we do see less cyclones simulated per season on average in the AerChemMIP runs. And this difference is mainly coming from improvements in the lysis latitude and the latitude change, particularly in the first 24 hours in the AerChemMIP runs compared to the coupled ones. So these box plots down here, and the bottom left, the pink and the blue bars are the AerChemMIP runs of CMIP6 and CMIP5 respectively. And these show quite significantly improved latitude change in the cyclones in the first 24 hours compared to the coupled runs, with the CMIP5 AerChemMIP runs actually doing better than the coupled CMIP6 runs in some cases. And there's minimal changes in the genesis latitude. So really seeing these cyclones move further polewards. And this difference appears to be associated with the surface fluxes associated with the cyclones from the ocean to the atmosphere. What we see in this case for over the North Atlantic is that, so in this case, because the flux is from the ocean to the atmosphere, it's negative. So red values mean the flux is too small. So all cyclones in the first 24 hours pass between this white and black dashed contour and interact with this red region here. So this region of anomalously low ocean to atmosphere heat flux of both sensible and latent heat, and this is associated with large negative SST anomalies in this region. And other studies have shown that this sort of SST anomaly is associated with cyclones being situated too far to the south in the North Atlantic, and it seems that this is also a contributing factor across the majority of the CMIP6 models. So now if we just do a bit of a focus on the Southern Hemisphere quickly. So this is the Southern Hemisphere summer that I'm showing you here. I'm showing you the summer just because the pattern's a bit clearer than in the winter season. Again, the structure of these panels is the storm track from the models is shown in the top left here. The CMIP6 bias here in the middle panel at the top, we see really quite small biases, some indication of a bit of an equatorward shift in the South Pacific sector, although this is nothing compared to the CMIP5 model shown at the bottom here, which had a very pronounced equatorward shift of the storm track around the entire hemisphere. And when you look at the difference between the two, we really see there's been a drastic poleward shift from CMIP6 to CMIP5, which is very much improving the state of the storm track in these new models. There's less of a difference for the two resolution categories of CMIP6 than there was in the Northern Hemisphere. In terms of the structure, they're quite similar. However, when looking at the peak intensity, so these top right panels up here again, we see that the high resolution models, these dark blue lines, do much more closely match the reanalysis than the low resolution models. So resolution does appear important for capturing the peak intensity of the cyclones correctly.
2 minutes.
Thank you. And then finally, just going on to what's driving these Southern Hemisphere biases, again, we examined the AerChemMIP models. The AerChemMIP biases to the reanalysis here in this left panel, quite minor in their magnitude. And when you look at them compared to the historical runs, we're seeing a further poleward shift compared to the historical runs. So again, improving the representation of the storm track compared to the coupled models. And we've tried to look at a bit why we've seen quite such a large poleward shift from CMIP6 to CMIP5. These bottom two panels here show the potential temperature at 850 hectopascals here in this first panel, and we see a large increase in the potential temperature around about 40 degrees south in the Southern Hemisphere, and associated with this is a poleward shift of the potential temperature gradient between 40 and 60 degrees south relative to the CMIP5 models. So the whole temperature gradient structure is shifting polewards, and the cyclones that are then forming along the temperature gradients are forming further polewards. This increase in the potential temperature in the mid-latitudes was associated with changes in the sea surface temperature from the CMIP5 to the CMIP6 models. As Pat was just discussing, there was positive SST anomalies in the Southern Ocean. We've actually seen that in the ensemble of models that we've investigated, this positive SST anomaly has actually expanded further equatorwards, especially in the Southern Atlantic and Southern Indian Ocean sectors. So that the SSTs are warmer, particularly in this region here where we've got the greener colours to the east of South America and to the south of South Africa. So the SSTs are increasing in this region, which is driving this potential temperature increase in the lower atmosphere. And this SST increase we've also associated with changes in the cloud feedbacks and cloud properties in the models. What we've seen is that the cloud forcing biases, which were too negative in the CMIP5 models, is now less negative and more in line with the observations, and we see a correlation of about -0.53 when we look at storm track latitude versus this cloud forcing in the 40 to 50 degrees south region. So it seems that as the cloud biases become more in line with observations in this sector, it's heating the lower increasing the SSTs and heating the lower atmosphere more, which is aiding the shift of the storm track further polewards. I'd just like to also point out that the evaluation of the CMIP6 models that we've performed has recently been accepted in Journal of Climate. Should hopefully be online in the next couple of weeks if you're interested in taking a look at that. But with that, I'll finish there.
Brilliant, thanks you, Matthew. So a couple of questions in the chat from Till. How reliable are the ERA 5 storm track simulations over the Southern Ocean?
So we compared ERA 5 to ERA Interim and also MERA 2 and JRA 55. ERA Interim and ERA 5 are very similar, as you might expect. The structure and the latitude are very similar across the other different reanalysis products as well. And there's slightly fewer cyclones simulated in MERA 2 and JRA 55. But this was something that was also noted with the previous generation of the reanalyses as well. But I would say that on the whole, the estimations from ERA 5, I'm very confident.
Right, thank you. And from Evgeny, how are the spatial patterns of the biases? How do they change for different seasons, particularly where you have sea ice biases?
So with relation to the sea ice biases, it's not something that I've looked at specifically just yet. I've mainly just focused on this region in the mid-latitudes. But we've also seen so this figure was for DJF, but in JJ and the other seasons as well, we're seeing this kind of equate with expansion of the SST anomalies. How much, what the relation is to the sea ice concentration as well, though, is something that will be looked at further in the future.
Brilliant, thank you. Okay, we better move on. There's a few more questions in the chat, so please have a look at those. So the next speaker is Rachel James from the University of Oxford, and she's going to be talking about LaunchPAD, developing and automating evaluation tools for Africa regions. Over to you, Rachel.
Hello, everyone. Thanks very much. Okay, hopefully you can all hear me and see my first slide. I'm going to introduce a new project called LaunchPAD. And the aim of this project is to improve our understanding of how CMIP6 models represent African regions. All but one of the CMIP6 models were developed outside of the African continent. But meanwhile, there is a great demand for climate change projections and information about future climate in African countries. And this has been recognized for some time. For example, the Department of International Development and NERC have funded over the last 4 years or so this Future Climate for Africa program, and the Met Office has also invested a lot of resources over the last decade, I would say, to improve their model over Africa. But one thing that we found during this Future Climate for Africa program is that to do this kind of process-based evaluation of the models, the kind of thing that we've heard about in the other presentations today, is very time consuming, and there's quite a bit of work to try and catch up for understanding African regions. And so we've been trying to think about how we can fast track this kind of work, and we're really excited to hear about these plans under CMIP6 to try to automate evaluation. However, there isn't at the moment many available tools which focus on African regions. So that's really the gap that we're trying to fill, to develop evaluation tools which focus on African regions. And the way that we're doing that is to connect UK modelling expertise with African climate expertise. So in the UK, it's between the University of Oxford and the Met Office. So Kath Senior, our chair, is a co-I at the Met Office and has led a lot of the ideas behind this, and is now co-investigator on the project. And then we're also working with 4 African universities where there are scientists who have a lot of expertise in the weather and climate of their region, but wouldn't necessarily have normally worked with CMIP6. And one of the ways that we're doing this work is through a fellowship program. And there are 10 early career researchers in these African universities who are funded for approximately a year each. And in the pictures here, you see our workshop, which we're happily able to do before the coronavirus lockdowns in February in Cape Town. And I'm going to tell you in a moment a bit about the research projects of those 10 fellows. And they're each working with this full-time software engineer based in Oxford, Tom Webb, to develop their code into software which can be run right across CMIP6 models, and hopefully will also be able to run in future generations of climate models, delivering a legacy of improved understanding of how climate models represent African regions. So this is our team. As I said, the project's being led from Oxford, but with a leadership team including Kath Senior, and 4 African universities with 5 co-investigators from the Kwame Nkrumah University of Science and Technology in Ghana, University of Yaoundé in Cameroon, 2 groups in University of Cape Town, that's Environmental and Geographical Sciences and Oceanography, and the University of Nairobi in Kenya. And each of those groups has 2 fellows. Actually, they were meant to be coming to the UK for a month-long visit. So we were actually planning that I think 9 of the 10 were going to be in Exeter today at the CMIP6 workshop and presenting some of their findings to you. Unfortunately, due to travel restrictions, that has not been possible. But some of them are listening online, so hi everyone. And I'm going to tell you a little bit about what they're each doing, and hopefully if we have these poster sessions again during May, some of them are going to present to you what they found about CMIP6 already. But just to give you an overview of which features and processes they're focusing on. For West Africa, we recognise that this is the part of the continent really where there's been the most model evaluation work to date. So, for example, within ESM-VALTOL, there are already some diagnostics which focus on West Africa. So in this region, we're really trying to fill in some of the gaps that aren't there yet. So for example, Thompson Anor has developed 3 really useful diagnostics which focus on the migration of the rain band, the heat band, and the West African heat low. Afia Akon is looking at the relationship between SSTs in the Gulf of Guinea, where models are known to have important warm biases, and rainfall over West Africa, particularly rainfall extremes in the more Guinea coast region. Makinde Akintunde, who's based at University of Cape Town, but originally from Nigeria, is looking at the West African westerly jet. Then in Central Africa, we have 2 fellows who Jerez Koite is looking at the African easterly jets, and then Thierry Taguela is looking at these low-level westerly winds that bring moisture from the Atlantic Ocean into the Congo Basin here. Hopefully you can see my cursor, and have been shown to be important for rainfall variability in Central Africa. Moving to Southern Africa, Ramontseng Rapolaki is looking at moisture fluxes into Southern Africa and developing diagnostics which focus on those. And we have 2 fellows that are working more in this Indian Ocean, Mozambique Channel region. Ronjotiane Baramalala is looking at the Mozambique Channel trough, and Paige Donkin is looking at tropical cyclones in the Mozambique Channel. In East Africa, Ellen Dyer, who is our research associate at Oxford, is looking at drivers of East African rainfall variability, and in particular she's found so far that easterly winds over the Congo Basin in Central Africa, approximately here, are really important for driving variability between climate models in the amount of rainfall in East Africa, and she's developed a useful diagnostic to look at that. And then finally, the two fellows based in Nairobi look at taking a more Pan-African approach, and Anthony Wanthi is looking at land surface coupling, whilst Oscar Lino is developing diagnostics to analyse moisture budgets across scales. So sorry that I'm not showing you any results today. It's a little bit limited on time, and also I wanted to let the fellows present their results themselves later. But that gives you an overview, and once this research has progressed, and in some cases it's already moving to the stage where we're developing tools which can be automated, and the way that we're doing that is to add them initially into the Met Office auto assess evaluation system. So this means that each time the Met Office model is updated, the usual auto assess evaluation system which is being run now or soon will have a lot more diagnostics which focus on Africa. And then that is also going to be included into ESM-Val tool, which I believe we're going to have a presentation about after lunch. This is being embedded into infrastructure to run right across CMIP6. So that's kind of our vision for how it's going to work. And yeah, hopefully more to come soon. And if you are working on any processes that link with what the fellows are doing, then please do get in touch. Thank you very much.
Brilliant, thanks Rachel. So there's quite a lot of questions just coming in.
Okay.
Now. Did you say which CMIP6 models you're using?
The idea is to run it across as many of them as possible. But for the initial phase, we've suggested that everyone, so all of the researchers, focus on 6 models to start with, and that will enable them to do some analysis without having to run their code across all of the models, which imposes some limitations in terms of either downloading data or running their analysis on Jasmine. And then it will be extended once the software tools are in place across all of the CMIP models that have the right data available.
Brilliant. And just a question from Colin about Cordex, and maybe a chance to say a bit more about how you're how we're getting over the difficulties in giving data to African scientists. Are we still sending it physically to them, or how are they accessing the data?
Yeah, I forgot to mention that. So we're using Jasmine, and we have a Jasmine group workspace, and that means that all of the fellows can access the, I think it's the BADC or CEDAR directories which have the CMIP6 data there. So we're trying to do some work to help locate that data, and in some cases they're using Jasmine to create subsets for the exact like latitudes, longitudes, years and variables that they want, and then downloading onto their own computer and doing the analysis. In some cases they're doing the analysis directly on Jasmine. It's kind of a bit of both. We kind of just got everyone working with Jasmine quite successfully at the time of the coronavirus lockdowns, and now it's become a little bit more challenging again because everyone's working from home. Some now don't have as good an internet as they would normally have. Some don't have access to the hardware that they would normally have. So we are kind of reassessing again, but so far Jasmine has been working pretty well. So thank you, Jasmine.
Yeah, brilliant. Thanks very much, Rachel. That's great. There's a few more questions if you can have a look in the Google Docs doc, but we missed.
Great, thank you very much.
Thank you. And our final speaker, just about on time, so hopefully Fiona, you get the full 8 minutes, is Fiona O'Connor. She's going to talk about assessment of the pre-industrial to present day anthropogenic forcing results from UKESM1 and AerChemMIP. Over to you, Fiona.
Thank you, Kath. Good morning, everyone. Just waiting for my slide to move across. So I'm presenting some work on the present-day anthropogenic forcing of climate. So this work's been done in collaboration with quite a large group of people who are contributing to the aerosol and chemistry model into comparison project AerChemMIP. So the motivation behind this work really is to better characterize climate forcings and their representation in global models. So we're aiming to quantify present-day forcings from a range of anthropogenic drivers using the UK's Earth System model, and we're exploiting simulations both from AerChemMIP and the radiative forcing MIP, which Chris Smith presented on yesterday. And between these two MIPs, it allows us to quantify quite an extensive range of anthropogenic forcings. So we're making use of the effective radiative forcing metric, which is represented here in the schematic. So it includes the instantaneous radiative forcing that would arise at the top of atmosphere in radiative fluxes, that would arise from an emission change, an emission of aerosols, for example, or a greenhouse gas concentration change. And it also includes rapid adjustments both in tropospheric and stratospheric temperatures, humidity, and important for some agents is the rapid cloud adjustments as well. And the table there is showing just a top level global mean ERFs from a subset of all the experiments that we've done. So moving on to the next slide, we can break down those anthropogenic forcings even further. So we have different groups of greenhouse gases in this bar chart on the left, speciated aerosol in the middle there, as well as the combined aerosol, tropospheric ozone precursors, near-term climate forces, which is combining the ozone precursors and the aerosols together. And we've land use as well as the total anthropogenic. And you can see here that our estimates of the present day forcing fit within these broad range of estimates from the 5th assessment report. At the bottom there, I'm also including global distributions of all the greenhouse gases on the left and all aerosol on the right. So you can see for the greenhouse gases, you might expect it's much more spatially homogeneous, positive mainly everywhere. Excuse me. The exception here is in the southern high latitudes, where ozone depletion and an aerosol response are offsetting the positive forcing from the greenhouse gases, and we have a paper submitted on that led by Olav Morgenstern. On the right then, the shorter lifetime of aerosols means that the spatial distribution of their forcing is much more heterogeneous, and you can also see that there are regions where absorbing aerosol is outweighing the negative forcing from scattering aerosol. So over the next couple of slides then, I'm going to focus mainly on methane. It's the second most important greenhouse gas after CO2. So here we're looking specifically at the present day ERF from changes in methane concentration since the pre-industrial. And the top plots from a paper by Gillian Thornhill shows that there's a factor of 2 spread in the estimates for the methane ERF at the present day from the AerChemMIP multi-model ensemble. In her second plot, she's breaking that ERF, which is represented in blue, she's breaking it down into the stratospherically adjusted radiative forcing, which she presents there in grey, and then the tropospheric adjustments, which she's presenting here in orange. And you can see that across this fairly small ensemble, there's a difference both in the magnitude and even in the sign of these tropospheric adjustments. UKESM1 is in the middle, and you can see that has a positive tropospheric adjustment, whereas all the others have a negative adjustment. So using a UKESM1, we've analysed the methane forcing in more detail. So in particular, methane is a reactive greenhouse gas, and so we've been able to apportion the total methane ERF from methane into how much is due to the direct radiative effect of methane and its rapid adjustments, and how much is due to the reactivity of methane and the coupling between the chemistry and aerosols. So you can see, for example, that the radiative impact of methane alone accounts for about 60% of the total forcing, and that Earth system interactions, including chemistry and aerosol interactions, are increasing the methane ERF by more than 50%. We also see that the aerosol cloud interactions and this coupling between chemistry and aerosol is driving a positive aerosol forcing, or a positive cloud adjustment in UKESM1, which is consistent with this positive tropospheric rapid adjustment assessed in the Thornhill et al. Paper. We also find that the tropospheric cloud adjustment is only positive when the aerosol cloud interactions are active in the model. Once they're disabled, our cloud adjustment actually changes sign and is then consistent with the rest of the AerChemMIP models. So in the next slide, we're going to explore why this adjustment is positive in UKESM1 in contrast with the other models. So when the change in methane concentration is applied in the model, this changes the availability of oxidants in the troposphere. And these changes in turn then alter the way sulfur is oxidized in the atmosphere. And in particular, the relative contribution of the three sulfur oxidation pathways changes. So for example, about 40% of the oxidation of sulfur dioxide occurs through this gas phase reaction with OH, and that the amount of sulfur being oxidized through that pathway reduces by 14% as a result of the change in methane concentration from pre-industrial to present-day levels. That is the only oxidation pathway that gives rise to new particles formation, and so the methane perturbation reduces the amount of new particle formation, alters the aerosol size distribution. So we see a reduction in the number of cloud condensation nuclei, a reduction in the number of cloud droplet number concentration, which is seen here in the bottom right. So we get fewer cloud droplets, but they're larger in size. So that makes the clouds become less reflective, consistent with a positive forcing from aerosol cloud interactions or a positive cloud adjustment. So UKESM1 was the only model within that AerChemMIP multi-model ensemble that includes interactive chemistry coupled to a two-moment aerosol scheme which models both aerosol mass and number. And our analysis of the methane forcing shows the complexity in chemistry and aerosol representation matters, and that chemistry-aerosol interactions can alter the sign of the contribution to the ERF from tropospheric rapid adjustments, particularly from clouds. And we might anticipate that as more models become available, there may well be other Earth system models within the AerChemMIP ensemble that also show these positive rapid adjustments. So although my focus here has been on methane, we have looked at other forcings, and indeed our other analysis of other forcing agents and drivers of climate with UKESM show that Earth system interactions are important in estimates of climate forcing. Thank you. Thank you for listening.
Brilliant, thanks very much, Fiona. So we've got a couple of questions on the chat, just a few minutes to ask them. So from Hyder, interesting that the Weddell Sea region seems to have a different negative greenhouse gas forcing to the rest of the Southern Ocean. Do you understand why this is, and does it relate to cloud biases in this region?
I can't comment on whether it's related to the the cloud biases, but we do, the ozone depletion is driving a poleward shift in the jet, and that then is altering the magnitude and the distribution of interactive emissions of both aerosol and aerosol precursors, which then gives us a cloud response contributing to the negative ERF there. So there is spatial heterogeneity in that aerosol response. So that may be a part answer to your question, Pat.
Thanks. And just one last one then from David Stevenson. How confident are we in the oxidant changes in UKESM1?
So that's a good question. We have reasonable confidence both in the changes in OH to methane perturbations. That's something that's quantified at least across a range of models, and UKESM would be consistent with that. Likewise, the tropospheric ozone response to methane changes again would be reasonably well characterized in models. So we have some confidence there. We would have less confidence in the response of the third oxidant, which is hydrogen peroxide, to methane, and indeed that accounts for quite a significant portion of the sulfur oxidation. So there is some uncertainty there.
Brilliant. Thanks, Fiona. I think we'll stop there. There's another question in the chat, so please have a look online for that. So thanks very much to all our excellent speakers today and this morning. That's been absolutely fantastic. Well done for keeping largely to time. So we will